0.5. Okay, we only have 2 lessons left for really the entire year. So we'll kind of gloss over them a little bit. The notes have a couple more examples than I'm going to do, or I'm going to kind of adjust the examples to do the highlights. So something to be aware of, on the printed out version of the filled in version of the note, there was a little mistake in the formula that I fixed, but in a hypergeometric distribution, which is the topic today, the main difference is that we are now looking at trials that are not independent. So everything up to this point has been a Bernoulli trial, which meant that they were all independent, they all had the same probability of success or failure. And now we're going to run into a distribution that we've actually seen already. We did this in the probability unit without giving it a name. So this is really a review lesson, and you could answer it using your probability methods, or you could answer with this formula. So this is when they're not independent. So this is when there are 2 things considered success and failure, but one actually plays into the part of the other. So just to be aware. So what this is sort of outlining here is the probability that some random variable x is going to equal something. This is going to be replaced with a number, this little x. Is the idea that you take the number of outcomes that you would consider successful and choose whatever number of successes you want. So this is telling you how many successes you want. So you take the number of possible outcomes that you consider a success and choose the number you want out of that. The number of possible outcomes that you are considering a failure and choose the rest. And then the bottom, as normal with the probability is n choose r, just take the total number of possible outcomes and choose the total number of objects you're actually choosing, or items. Okay, so it looks a little bit confusing. A is the number of successful options, so that's dependent. If it's a card question about black and red cards, or it's a dice question about even and odd, you're still looking at success and failure, but this A and B is telling you how many successful outcomes. So it's a card question about red and black. You'd have 26 red options, 26 black options, but you're probably dealing 5 of the cards. Okay, so then X. So say you had a question, determine the probability of drawing exactly 3 red cards. You'd take the 26 red cards and choose 3. You'd take the 26 black cards and say you're getting a hand of 5. You'd choose exactly 2. So then on the bottom, you're taking the 52 cards and just choosing any 5. Okay, so we've done questions like this before, but without the complicated formula. In the past, people have preferred to just answer it straight away without actually identifying what all the variables represent. They can think about it in terms of a probability aspect a little better that way. Okay, expected value in this situation is talking about the number of trials you're doing multiplied by the number of successful options you have over the total number of options. Okay, so R times A divided by N. So these are the 2 formulas you're going to be using in hypergeometric distribution. And again, because we're doing it online and because there's no one there to really assist you, I'm really trying to drive the focus of, here's the formulas, maybe make a nice formula sheet before you do the assignment. You're really plugging them, identify what type of distribution it is, and then it's just a matter of plugging the numbers in and solving. Okay, example 1 that's listed here, this is a typical question that we've seen before, where you have 2 groups, distinct groups of people. So this is men and women. You have 8 men and 10 women, so 18 people total. And you're trying to select a jury of 6 people. Okay, so obviously there's all kinds of combinations of ways you can select a jury of 6 people. You can have all men, you can have all women. You can have a combination, 3 men, 3 women. You can have 4 men, 2 women. Obviously there's unending number. So in the question on the actual note, it says, calculate the probability distribution for the number of women selected. When they ask you for a probability distribution, they're asking you to find all the options. Well, all the options would mean we'd have to find the probability of 0 women, 1 woman, 2, 3, 4, 5, and 6. I'd have to do 7 calculations in front of you. Okay, is it hard? No. Is it time consuming? Yes. So I'm breaking it down, and I just want to find the probability there are no women and find the probability there's exactly 1. From there, if you want to calculate 2, 3, 4, 5, 6, then you can figure it out. So if we use this formula here, what we want to look at is n is the total number of people we have. So we've already discussed that there are 18 people to choose from. That the n value doesn't put them into groups. It's just how many do you have to choose from. R is telling you how many trials you're going to do. So basically, how many things are we actually selecting? So in this case, we are selecting exactly 6 people from those 18. Okay, so when you're doing the calculation here, the denominator is always take the total number of people you have, or objects, and how many you're selecting, without regard to any groupings. Okay, so this is non-committal to saying men versus women, red versus black, hearts versus spades, none of that. So that would be in the denominator. Now the top is what you consider successful. Because we are considering selecting a woman as being successful, A is the number of women we have to choose from, so that's going to be 10. B is the number of things we consider a failure, which in this case would be men. Okay? And X is what we want. So because we want 0 women, we're considering our X value to be 0. So when you look at this formula, it says take what you consider successful, women in this case, of the 10 women, and choose however many you want. So of the 10 women, we are choosing 0. Of our failure, which is men, we then have to choose 6. Notice this is similar to what we did before. The 10 and the 8, the two numbers that are on top, A and B, have to add to be equivalent to n. Okay, these two numbers have to add. 10 plus 8 is 18. Okay, and then the two numbers down here, x, and what we're considering r minus x, obviously 6 minus 0, have to add to be r, which makes sense. If you just added this, x plus r minus x, the x's go away and you're just left with the r. So that's a way for you to check. Now, in order to calculate this, you just put it in your calculator. So you'll do 10 choose 0. Okay, so you have to have a calculator that can do this. 10 choose 0 times, maybe put it in brackets just to make sure you don't make a mistake, 8 choose 6. Okay, when I look at that, it's the number 28. From there, I can just press divided by, and then again, maybe use brackets just to make sure it doesn't mess up. 18 choose 6. And I get the chances that we get no women on the committee is 0.1%. Okay, and that makes sense. Like, because there are 10 women in a group of 18 and you're selecting 6 people, chances are you're going to get a woman somewhere. So the chances of getting exactly none is 0.0015, which is 0.15%. In what I've created as example B, find the probability you get exactly 1 woman. The only thing that changes in your calculation, you still have 18 choose 6 here. The only thing that changes is now you're saying of the 10 women, I want to select exactly 1. Of the 8 men, how many do I then need? Well, if I've already selected 1 woman for my jury of 6, then I can have exactly 5 men. Okay, and then just look at the addition. 1 plus 5 is 6, 10 plus 8 is 18. And when I actually calculate this, 10 choose 1 times 8 choose 5 divided by 18 choose 6, I get 0.0302. So now you have a 3% chance of getting exactly 1 woman. Also unlikely, but it could possibly happen. Okay, now the other part of this question said, the actual part B of this question said, what's the probability there are at least 2 women? So I just want to remind you, at least 2 women means 2 or 3 or 4 or 5 or 6. 5 different options. If you use the direct method, you have to do 5 calculations. Be aware of the indirect method. It's done for you on here so you can look at it. The indirect method is total minus opposite. Okay? So total in this case, basically being 100% chance you select someone, so it's always going to be a 1, minus the opposite of at least 2 women. So the opposite of at least 2 is 0 or 1. Well, we already calculated 0 and 1. So if we add the probabilities for 0 and 1 together and subtract them from 100% chance we select someone, then that will give us the probability you get at least 2 women. But it's up to you. You can do 2, 3, 4, 5, 6, 5 calculations, or you can do 2 calculations and subtract them from 100% chance that something happens. Okay? Totally up to you. All right, so that takes care of the first example. The second page, they introduce the formula for expected value, which is fine. I am going to move on to example 3. I'm going to keep my formulas up here. I'm just going to work on the lower half, just so they're there and I can see them when I'm doing the calculation. This is probably the lesson that people find, I don't know, maybe the easiest in the unit, only because we've seen it already. We just didn't give it a name, so it's really 100% review. Okay. Example 3 says, how am I on example 3? What was example 2? Example 1? Oh, example 2. Calculate the expected number of women. Okay, whatever. Not important. Okay, calculate and graph the probability distribution for the number of spades dealt if 3 cards are dealt. Okay. So you're looking for the state when dealt 3 cards. Does not look like a 3. Okay, they want the entire probability distribution. When they say they want the entire probability distribution, they want all the options. So if you are being dealt 3 cards, what are all the options for the number of spades you could get? You could get 0 spades. You could get 1 spade. You could get 2 spades, or you could get 3 spades. So in a situation like this, if they ask you for the probability distribution, you have to calculate all the possible options. Is it annoying to do 4 calculations? Of course. But you get the idea. So here, when you're looking at this formula in terms of what everything is, spades is what we are considering a success. So how many spades are in the deck? Well, in this case, we would say the number of spades, I'm going to go right down here, which is what we consider a success. There are 13. There are 13 of each suit. What we consider a failure is anything that's not a spade. Okay, so hearts, diamonds, clubs are all considered a failure. 13 plus 13 plus 13, 39. What do these miraculously add up to? 52. That's the total number of cards we have in the deck, which is our N value. Our R value is how many we want to select. Well, how many cards are we being dealt? 3. And our X value is changing depending on which one we want. So we're actually doing an X value of 0, 1, 2, and 3. We're looking at all 4 options. So when you do the calculation, you're simply plugging these numbers in. What's changing is this value and this value. All the denominators will be the same. All the denominators will be of the 52 cards, deal 3. Of the 52 cards, deal 3. Okay, that does not change. The top number in the combination does not change. In all of these, we're saying 13 spades, 39 other cards. 13 spades, that's what we consider a success, 39 other cards. 13, 39. And again, what's going to change is how many successful outcomes we get. In this case, we're specifically looking for 0 spades, which means of the 3 cards we're getting dealt, how many other cards are, or how many cards are not going to be spades? Well, if 0 of them are spades, then all 3 of them must be failure cards, hearts, diamonds, clubs. If 1 of them is a spade, then 2 of them must be failure cards. Remember, these 2 numbers have to add to this. If 2 of them are spades, 1 is a failure card, and if all 3 of them are spades, 0 of them are failure cards. Okay? So, I'm not going to put this all in my calculator, it's right here, but you get the idea. Multiply the 2 combinations, divide by 52, choose 3. This one said there's a 41% chance of getting no spades. There is a almost 14% chance of getting, oh wait, hold on, that's wrong. That's 2. Probability you get 1 is almost 44% chance. Probability you get 2 is 13.8. And probability you get 3 is 1.3%. If you want to graph it, remember the probability distribution graph is just the idea that you put your x values down here and you put your probabilities here. So we had x values of 0, 1, 2, and 3. Our probabilities, because we only go up to a maximum of 43%, we can just list the probabilities up to 50 basically. And then you're just drawing a line up. So probability you get 0 is 0.41 something. Probability you get 1, 0.43, a little bit higher. 2, 0.13. Then this one, 0.1. Okay, so that's what the probability distribution graph looks like. I'm probably not going to make you do one of those, but. Okay, and then the last part of the question, which was question B, said, what's the expected number of spades you get? Well, expected number just says, use the formula we have here, R times A divided by N. So our R value, again, we know. We're selecting 3 cards. How many are successful? 13 of them out of 52. So when we actually go and calculate that, your chances are that you're going to get 0.75 of a spade. Well, obviously that makes no sense because you're only able to deal whole numbers of cards. But it's basically saying around 1. Okay, so of the 3 cards that you are being dealt, you would get around 1. If you were being dealt 4 cards exactly, your expected number of spades would be exactly 1, because you'd be expected to get 1 spade, 1 club, 1 heart, 1 diamond, all with equal probability. Okay, because you're only being dealt 3 cards, that's why that goes down a little bit. Okay, so I think you kind of get the idea of what's happening here. Okay, we will do the last example, and then that'll be it for 5.5. I'm going to, yeah, I don't need to keep this up. Okay. In the last example, they want a hat contains 20 names. Names in a hat. Also, they tell us 12 are female. 5 names are drawn. Find the probability at least 2 are female. At least 2 means greater than or equal to 2. Just going to analyze this as female, okay? So we want to find the probability that at least 2 are female. And so we have 2 options. We can find the probability that 2 are female, or 3, or 4, or 5. We can do 4 calculations like we did on the last one. Or we can use the indirect approach and say the opposite of at least 2 female are no females, or 1 female is the opposite. So we can do 100% minus that. So I would suggest that indirect method. That's why I didn't do the example on the other one, because this is the same thing. So probability that x is greater than or equal to 2 is 1. You're always using 1 because there's a 100% chance you get something, minus what we consider the opposite. So remember the opposite, and I'm going to put this in brackets, is the probability you get 0, or, and remember, or you add the probability you get 1 female. That's the opposite of more than or equal to 2. Okay, so what we have to do here is actually calculate these 2 things to be able to plug them in. So we want to find the probability you get no females and the probability you get exactly 1. So without using that big formula, without even thinking about the big formula, just really analyze what this is asking. There is a group of 20 people. You are drawing 5 names. So your denominator, without regard to any restrictions on what are the successful and failure things, it's just 20 choose 5. 20 choose 5. Now in the numerator you split them up into success and failure. So we're considering a female a success. Okay? So of the 12 females we want to choose 0. Well, it doesn't tell us how many males there are. But if there's 20 people's names in a hat and 12 of them are female, that means 8 of them are male, and we want all 5 of them in this case to be chosen as male, because we want 0 females. On this one, the only thing that changes is, of the 12 females, we choose 1. Of the 8 males, then how many do we get to choose? 4. And when you actually go and calculate this, this one is 0.0036. This one is 0.054. So when we plug it into this part of the indirect formula, we will add them first and then subtract them from 100%. And in the end, we'll get an answer of almost just over 94% chance that we get at least 2 females. Okay, remember there's 12 females out of 20. There's more than 50% of them are females, so there's a very high probability you get at least 2 of them. Okay, so just a little bit of review about the indirect method. But otherwise, this is very highly, this is very similar to what we did in chapter 2. So I think for a lot of you that did well in chapter 2, you'll look at this and go, yeah, I remember this. Plus it's a good review because we are going to have a culminating where we have to kind of remember some of our skills from the rest of the unit. Okay, good.